So today we're going to look at the CME 2 7.1 frequency analysis tool. If you got a plus drive and updated firmware, you should be able to gain access to this new tool. This will do a sine sweep. I'm going to look at first the closed loop current, but we can also do open loop velocity. So, we want to check out some resonances in a system here. We can start at a frequency, end at a frequency, do some number of steps, and hit start. And the firmware starts to gather the data by sweeping the frequency and looking at the magnitude, gain, and the phase. And you can hear it a little bit here. I've got a Sanyadanki motor with a high count, 131,072 counts per rev. I got a gear, maybe it's like a 3-to-1. I got a belt on this system here. This is H-bot or a T-bot, and so this piece, the orange piece, moves, and I'm just holding it still at the end here. And I'm using a BEL ExcelNet Plus drive to do the testing. So you can see that the gain of the current loop is flat, and it goes out and then starts to roll off. We've got a minus 3 dB point here at about 400 hertz. That's a little sluggish. I like about a kilohertz of current loop bandwidth, and then the phase starts at 0 and rolls off. Had we gone further, you could see where the phase shift was 180 degrees. So lots of gain margin, lots of phase margin here. Phase of 0, gain of 1, and you got a resonator, so you got to stay away from that. But we're going to take a look at what we did here to get this current loop, and then we'll investigate the velocity loops after that. So I started with the Sanyadanki motor data, inertia. I didn't add the load inertia, so I'm just working off the motor inertia. The values that originally are used here are calculated by a math model based on the data we input. So we get some, pretty good values here. I may have a mistake with entering my data. Maybe it's, 4.3 millihenry phase to neutral. Well, the inductance is phase to phase, so maybe it's really 8 millihenry across the pair of wires. But that's okay. We're going to tune it. So we get, some pretty good data, get a pretty good calculate. You can see the calculated values of CP and CI are not nice round numbers. So they're like, very, 31, right? I do 30. So these are not human numbers. These are calculated numbers. So normally when I tune the current loop, I apply a current auto setup checkbox, hit start, small signal, and set my interval to 0. Let's go for double the current loop gain. I'm looking for the point at which I get an overshoot, and 4,000. So I'm starting to get a little peaking here. So there's a little overshoot. So I'm just going to cut this number in half. Yeah, it's a large inductance. I got a slew rate limit. If the interval term is too high, you'll get interval wind up and overshoot. You can see the slew rate limit there. I'm running this 8 millihenries with 26 volts, so it's a little droopy there. So the goal is to get the steady state without much interval overshoot. And this looks pretty good here, 1,500. And I'll hit stop, and then we're going to try the frequency analysis tool again and see what the sweep looks like here. Okay, so the current sweep now is flat gain, goes out and rolls off to about 1.2 kilohertz of current loop bandwidth. So this is a good way to gather frequency over time data, or phase or gain over frequency. So out of the time domain into the frequency domain. And then, of course, you can save the plot to a file and open it up as a comma separated value file for analysis with other tools like MATLAB. So now we're going to take a look at the velocity loop. Auto setup checkbox, command and actual velocity. Here's the gains. These are the calculated values. You can see the system is shaking and baking over here, rocking and rolling. So that's the calculated values. So when we do the frequency analysis on the closed loop, so this is the closed loop velocity sweep. Goes out pretty flat, then rolls off. Starting at phase 0, I got a 180 phase shift here at about 100 and something hertz, and I'm down 15 decibels, so no oscillations. There's a little blip here around 50, 60 hertz. We'll investigate that further, but you know, you start rolling off just before 200 hertz. This is explained by the pole at the output of the velocity loop. It's a 2-pole. We can switch it to a single pole, and that'll move out. So we're going to take a look at the tuning of the velocity loop in the normal way now, and we'll see what we can get out of this tuning here. So again, if my gains are too high for my BP, I'll start seeing ringing. I moved the pole to a single pole, give us a little phase margin. In the next sweep, we should see the, there you go. So the location of the filter frequency and the gain. Again, that's a little ripply, the gain's a little high. I like to bring it up to oscillations and then cut it in half. So let's just check it out again to make sure that we got not too much resonance. There's a little ringing going on here. I'm going to move the pole down here, single pole, moving 200 hertz. It's a very mechanical system here, so there may be lots of resonances. So we're going to do open loop velocity with a stimulation current of 175 amps, 1.75 amps. The start frequency will be at 1 hertz and go to a kilohertz with 100 sample steps. How can you do open loop, you might ask? Well, you have to close the loop and put an excitation in and look at the output over input to get the gain and the phase margin. So that's kind of a bit of a trick, but we're going to see how that works. So we'll start with a really low frequency and start gathering the data. So, skipping ahead here. Some kind of resonance there. Oh yeah. All kinds of mechanical resonances. So here's the open loop gain. We got 5 dB. Goes out flat. There's a little funny business between 20, 30 hertz here. There's another funny business around 100 and, I don't know, maybe 15, 20 hertz there, and then rolls off. So these are, looks like sort of mechanical places of resonance. We get about a 3 dB around the 200 hertz. That's the output of the velocity loop pole. And we got some phase shift here. I guess starts at about 180 and flips over around 0 here. So the gain is less than 0 at this point, so we have stability. But we're probably getting a little bit of integrator windup there. I pushed the integral on it to flatten it out, but there's a 0 to extend the velocity. So I'm going to cut that down a little bit, and maybe let's try a notch at this frequency here and see if we can notch it out. Okay, so here's a notch filter with a cutoff, at 100 to 150, and then I did the sweep, and you can see, yeah, it really is an effective notch. I no longer get the bump up there, but I think maybe I'm just going to try a lower frequency pole here. I had a 50 hertz oscillation, so maybe if I used a 50 hertz pole there, we could still get stability. So we'll take a look at that. So I'm trying to pole at 25 hertz. I got rid of the notch, and if we look at the phase shifting from 180 down to 0, and then look up at the gain, we're down to minus 30 decibels. So lots of gain margin, lots of phase margin. And we go off pretty flat and roll off heavily here, but the resonance around 50 hertz it's a lot of mechanical stuff going on here, so there's a little funny business. But one school of thought is reduce the bandwidth so that you don't excite anything, and the other is when you get disturbed, have high bandwidth to correct for it. So I'm just going to make a little move. You can see the disturbance in the mechanical system 4 times per the move. A little S-curve would be better. I'm actually pushing into a load here, so I got a little integral to steady state. But there's the bounce, 25 hertz or less based on the mechanical system. So this feels very well behaved, no big jerking, just normal tuning and settling. Okay, so here's with the pole at 300 hertz, single pole, high gains, and this is rather well behaved. I think I like this tuning a little better. If there's a disturbance based on the mechanical system, we have gains to make corrections. So much for the 25 hertz. I think that's acceptable, as it's not a large inertia on here yet, and we get some pretty good tuning with high gains. So let's move the pole out, crank up the gains, get maximum stiffness. There's a little disturbance in there, but hey, we can see it on the frequency analysis, and we can avoid it or we can correct for it. Thanks for watching.